All right, everybody. Thank you for joining. How late do we have until? Do we stick them by the timeline? Are we skipping the Q&A, or what do you think? Shorten Q&A. Okay. All righty. Well, thank you everybody for coming. I think there's so much excitement. I'll skip the intro other than to say we have Dr. Wang here, who's a nephrologist and clinical geneticist at Cleveland Clinic and runs a very successful nephrogenetics clinic and program. So without further delay, go ahead.
Okay, cool. First of all, my apologies that we got a little bit late. So I will try to catch up on time. Again, we might skip the QA, but if you have any questions, please feel free to stop me during the break or lunchtime. Okay. So today I want to give you a review of genetic primer. What I'm going to talk today possibly are not something that you never heard of. My job today is to refresh you and remind you. Okay, so what we are going to talk in these next 30 minutes or 35 minutes, I want to have a review about the history of genetics, including the clinical genetics and renal genetics. The reason I want to talk about history is because I believe when we know better about the history, we will have better idea about the future. Next, I would like to review some basic genetic concept and knowledge. As I said, now this that I would talk are something that you never heard of. Is just to remind you and refresh you. At the end, I'd like to spend about 10 minutes to talk about the genetic testing from technology perspective based on the knowledge and the concept that we are going to review to help you understand the clinical testing and what testing option would be best for your patient in your practice. Okay, let's get started. I like to quote Dr. Eric Nielsen. He said in 2000, 25 years ago, probably nothing in the field of medicine is moving more rapidly than genetics. And nephrology, we often do not agree with each other, but I guess this is something we all agree on. When we talk about the history of genetics, really started in 1859, when Charles Darwin wrote On the Origin of Species by Means of Natural Selection or the Preservation of Fewer Races in the Struggle for Life. And his proposal was supported by Mendel's experiment on peas that heredity is transmitted in discrete units, explaining how natural selection could work, and again provide support for Darwin's proposal. Something you may not know is that Mendel died at the age of 61 from chronic nephritis. So after the groundbreaking work from these two giants, the history of genetics really started and moved quickly. In 1869, the DNA was for the first time isolated from the pus of the yeast banded by a Swiss physician and biologist, Dr. Mayer. Dr. Mayer was a former student of Dr. Kossel, who was a German biologist. And Dr. Kossel received the Nobel Prize in 1910 for his pioneering work on DNA. He also coined the word DNA. That's how we start to use the word DNA. And the history hit 20th century. In 1902, British physician Dr. Garrod observed that alkaptouria, that is the inborn error of metabolism, if the urine gets exposed to the air, it will become black. So he observed this disorder follow a Mendelian rules. That was the very first medical condition ascribed to a genetic cause. This also marked the beginning of the clinical genetics. Time continue move to 1909. The word gene, we talk about gene genetics all the time today. The gene first time being used in 1909 by Dr. John Hansen. He was a Danish geneticist. He also coined the word genotype and phenotype that you will continue to hear in today's talk. The gene came from the word, Greek word genos, meaning birth. So moving to 1950, we all know that Dr. Francis Crick and Jim Watson described the double helix of DNA, and they received the Nobel Prize. And in 1955, Dr. Thiel and Dr. Levin collaborated and discovered that we correctly counted that human have 46 chromosomes. Before that, we saw that human had 48 chromosomes. Continue moving. In 1961, Dr. Gharavi developed a method to test the newborn for the metabolic defect PKU that laid out the foundation for the newborn screening. Now we use the worldwide and save the numerous lives of babies. Continue moving to 1975, the two groups, including Dr. Sanger and his colleague, collaborated and developed a rapid DNA sequencing method that made the human genome project possible. And just 1 year later, the very first biotech company, GenTech, was founded. And now is worth, I checked the Wikipedia, is worth more than 26 billion with over 13,000 employees. The collaboration between clinicians, scientists worldwide got further deepened in 1982 when scientists began submitting DNA sequencing data to an NIH database gene bank that is open to the public. And in 1983, a genetic marker for Huntington disease was found on chromosome 4 that marks the first disease gene ever mapped. And just 2 years later, Dr. Rieder and Dr. Wezro group from Germany, they identified a highly polymorphic DNA marker linked to ADPKD that marked the beginning of renal genetics. Time moved to 1990. This is something we all know, as the Department of Energy and NIH announced a plan for a 15-year sequencing project to sequence the human genome. And they planned 15 years, but in 2003, 2 years earlier than planned, they completed the sequencing and finished the 3.2 billion letters of the human genome sequencing. Moving the scope and focus on renal genetics, as I listed here in this busy slide, you can see our scientists and nephrologists are very busy in the discovery and very productive. From 1985, that we said ADPKD gene first time being mapped, to 2019, Dr. Ali Gharavi's group conducted the whole exome sequencing in a large cohort of CKD patients. I identified just near 10% CKD patient has a genetic diagnosis. That's really marked the landmark. So while our scientists and physicians are busy, productive in their research, they also collaborate with the community and advocate for the policy change. In 2008, Genetic Information Non-Discrimination Act, also known as GINA, was passed. At least the voting result there, overwhelming. It's just something you would not imagine now. It's overwhelmingly passed by the Senate and House and signed into law by President Bush. The act bars the use of genetic information in health insurance and employment. This really paved the way that we can bring the genetic discovery into the patient care. Although this act has some limitations, it does not cover life, disability, or long-term care insurance. If you work in a small business with less than 15 employees, sorry, you are not covered. And it does not apply to individuals receiving their insurance through the federal government or the military. So we still have a lot to do to advocate for our patients and for ourselves to get fully protected. In 2015, in the State of the Union address, President Obama, possibly you all remember this moment, President Obama announced that he's launching the precision medicine initiative that was defined as an emerging approach for disease treatment and prevention that takes into account individual variability in genes, environment, and lifestyle for each person. And 10 years later now, 2025, genetic is becoming visible and profitable. If we look at the cost of DNA sequencing, the first genome sequencing cost $3 billion, and now dramatically changed, declined to just a couple $100 for the panel testing, as we all know. And the human genetic evidence supports 2/3 of 2021 FDA-approved drugs. Also, more than a dozen gene therapy, including the one small interference therapy for the primary hyperoxyuria, like our patient Nancy mentioned, are on the market now, and more than 1,800 gene therapies in clinical trial all over the world. So indeed, the genetics is now. Looking at the history of what we have learned, we see the talents collaborate doing innovation, and also the advocate strongly for the policy change to bring the genetic discoveries into the patient care. I believe this has shaped our history, and I believe if we continue to do this, we will have a brighter future. Although, yes, we have a lot of challenges. So let's go back to the basic genetic concept. I always like to tell my daughter and my students that a journey of 1,000 miles really began with a single step. So let's talk about something very basic. We know this morning all the talks talk about the family history is an indicator for considering genetic disease. So it would be good you have some understanding about the family tree, also known as pedigree. Particularly if you work with a genetic counselor, they might present you with a pedigree. So it's good to have some basic understanding about this. The pedigree, by definition, is a graphical representation of a family, showing the relationship among individuals and their medical and demographic information, as an example like this. When you look at the pedigree, the horizontal rule is a generation. The Roman numerals are for generation. The Arabic numerals are for individual. The siblings will be listed with the oldest to the left. And if you have space, the name or age of each individual will be written down. And of course, their medical history. This is the standard pedigree symbols as listed here, like the square represent the male, the circle represent the female. For the affected, the square and the circle will be filled with color. There is a pointing arrow to the proband, and the horizontal line connects two individuals in marriage or union. If you see two lines, that means they have consanguinity. So we talk about consanguinity. That means a mating between biologically related individuals. If you read the literature, you possibly read the proband, consultant. Are they same? Not always. Proband meaning an affected individual come to medical attention independently of other family member, that they are the first one coming to see the doctor. And the consultant is your patient. So your patient might be the proband, may not be the proband. The degree of relationship, here I listed some examples, is defined by the cycle of meiosis. The first degree often refer to parent-child and siblings, and second degree is grandparents to child, uncle child, and third degree often are the first cousins. When you look at the pedigree, you need to ask yourself two questions. One is this dominant or is this recessive? Dominant means no difference between male and female. X-linked, that means there is some difference. And then after that, you decide is this dominant or recessive. So with this, you have 4 types to consider: autosomal dominant, autosomal recessive, X-linked dominant, and X-linked recessive. I will also touch on the mitochondrial inheritance pattern a little bit too. Talking about autosomal dominant disorder, this is the typical pedigree you would see for a patient with ADPKD. They follow the vertical penetrance. You see the disorder transmitted from generation to generation. No difference between male and females. They're equally affected. Most mating are between normal individual and heterozygous. The risk of their children are 50%. Turning on the autosomal recessive inheritance, this is something you could see in your patient with ARPKD. They follow the horizontal transmission. The affected patients are often siblings or part of the same generation. You do not see that through the generation. So if you do not see a family history, you cannot completely rule out, oh, this is not genetic, because autosomal recessive disorder, and particularly for those with a small family, not a lot of siblings to tell you, then you might consider autosomal recessive. And because it's autosomal disorder, you don't see the difference between male and female. Both parents of affected child presumed to be carriers. They are obligated 100% carrier. And risk for their future children to be affected is 25%. We talked about these 2 lines, meaning the consanguinity. This is often being seen in patients with autosomal recessive disorders. Sometimes we see occasionally found at high frequency in certain genetically isolated population. Sometimes a single allele, like the R229Q in MPHS2 gene, they are pretty high dominant in certain populations, have been passed down from a common ancestor. It's called founder effect. Moving on to the X-linked dominant inheritance, today you possibly will hear some talk on this too. Because it's X-linked, number one rule is no father to son transmission, because they get the X chromosome from mom. And all daughters are affected, males are affected because all daughters get one X chromosome from the dad, so they are all affected. The offspring of affected females have 50% chance to be affected because the kids can get one chromosome, one or two chromosome, one out of two chromosome from mom. Affected female usually have a milder phenotype. Sometimes you see a male lethal paucity of male. You see no male family member in the family, or they died in the early childhood. One example is the X-linked hypophosphatemic rickets related to the PHEX gene. Moving on to the X-linked recessive inheritance, one example is the Danon disease. Because it's X-linked, it follows no father to son transmission. They follow the diagonal inheritance pattern. Affected males are raised through the female in the maternal line. All daughters are affected. Males are carriers. Females may occasionally express the disease phenotype. Here I would call your attention is some disorder like Fabry disease, X-linked airport disorder. We previously thought they follow the X-linked recessive inheritance, but now we know not always the case. The female patient could present with symptoms or even severely affected and developing into end-stage kidney disease. So now we call that as X-linked but not recessive disorder. A little bit of touch on the mitochondrial inheritance because we now realize that mitochondrial disorders could affect the kidney, particularly the renal tubules, and sometimes some patients even present with FSGS. So when you look at the inheritance pattern for mitochondrial disorder, because mitochondria exclusively get from mom, so you get that from a maternal line. Both male and female can be affected, and this disorder is transmitted again through the female to her offspring. If you have a male patient with mitochondria, just like we had one patient presenting with FSGS, and we found a mutation in the mitochondrial DNA, we told him, one good news is that all your 4 kids won't be affected. So the affected male do not pass the affected status because it's the mitochondria. All right, let's continue. We talked there about the family history that is important for you to narrow down your differential. And then you consider, what test I should do. So let's move on to the basic of genes and chromosome. We talked about when the gene was identified being coded and chromosome. We know genes are made up of DNA. Humans have about 25,000 genes. And now we can sequence that with the whole genome sequencing. And over 5,000 medically related genes. They cannot be seen under a scope, but we can test that through the sequencing or some other technology. The chromosomes are made up of genes. Humans typically have 46. As I said previously, we saw we had 48. In most of the body cells, they can be seen under a microscope. That's why Dr. Teal and Dr. Levin are able to correctly count the number of human chromosomes. So all the genes are composed of exons and introns. Exon also known as a coding area, intron also known as a non-coding area. The mutations, or now we call that pathogenic or likely pathogenic variant, affecting gene expression can happen in exons, can happen in the exon-intron boundary, or they could happen in the upstream regulatory region or promoter region. Important to remember is the sequence of nuclear DNA is nearly 99.6 identical between any two humans. Some DNA sequence difference have little or no effect on phenotype. others are directly responsible for causing disease. So there are two extremes. Only these two extremes is the variation responsible for genetics determined phenotype, phenotypic variability. Genetic disease only caused by the obvious and extreme manifestation of the genetic differences. Of this variable portion of a human genome is only 0.4%. So there are three types of variant. Variant, you could consider that as a change. Variants can be the mutation. Previously, you hear the mutation all the time. Mutation, now we define that as the pathogenic or likely pathogenic, the variant. Most of the time, these variable portion of genomic variant, there are three types. One is single nucleotide. That's the most common type of the variant. Second is the small insertion of deletion that usually involve less than 50 nucleotide. And third one is a structural variants. So I will talk, the reason I talk with you about this is to help you understand why some disorder you need to do the sequencing test, and some you need to do additional test, and why different tests have different coverage. Talk about the single nucleotide by name is only involve one letter. As we show here, it's only one single nucleotide in the genome sequence is altered. It can be either common or rare. When the single nucleotide variance, the prevalence is over 1% in the human population, is called a single nucleotide polymorphism SNP. Okay. It can occur in germline. All the talks today will be focused on the germline. But as you know, in the oncology, they test a lot of mutations in the somatic, in the cancer cells. So the single nucleotide variant can happen in the coding, in the exons, or non-coding in the introns. When it happens in the coding area, it could be non-synonymous. That means there will be a change in the amino acid sequence. And it could be synonymous, that means no change in the amino acid. When it's non-synonymous, it could be missense. That means one amino acid is substituted by another one. Or it could be nonsense, like Nora showed you, the nonsense mutation over there. That means there is the introduction of the premature stop codon that stops the gene expression. Of course, the translation of the protein stops too. That will cause the dysfunction of the protein. Moving on to the insertion deletion, we talk about single nucleotide is only one letter got altered. The small insertion deletion often involve less than 50 nucleotide. It could be a short string of nucleotide becoming inserted and or deleted from the DNA sequence. It's the second most common variant. Moving on to the structural variant, we talk about single nucleotide as 1 and small insertion deletion 2 to 50, and structural variant often involve more than 50 nucleotide. Okay, it can be classified as deletion, as you see here. The deletion meaning that a piece of genomic information got lost, or duplication. That means actual copy being added, or it could be inversion. Often is a piece of chromosome got inverted. Or it could be translocation. That means one piece from each chromosome got translocated. So often these three would not cause the dosage change in the genetic material. We call that rearrangement. One subtype of structural variant need be known is called copy number variants, because now we realize copy number variants could be related to the genetic disorder, and about 3% genetic kidney disease are caused by copy number variants. It's often being represented by the deletion and duplication. As I said, compared to the translocation inversion, this deletion and duplication often involves in the dosage change of the genetic material. Again, the structural variants often have the size over 50. And here you see the copy number variant, they often involve the nucleotide from 1 kb to 1 megbase. This basic knowledge here I show you is because when we pick the right test, you know their resolution. So you know if this technology could actually pick this genetic change. As I said, the copy number variant actually accounted for about 3% of cases with genetic kidney disease. So we know the single nucleotide variants are very important. It's the leading cause for genetic kidney disease, but copy number variants are also important. So with the understanding of the basic concept and knowledge, let's move on to the genetic testing. So how we detect this. The single nucleotide variant and small indels can be detected by sequencing, okay? Because they often involve less than 50 nucleotides, they can be accurately picked by the sequencing, either Sanger sequencing or next generation sequencing. Sanger sequencing was developed, as we said, by Dr. Sander and his group. It's a chain termination PCR with over 99% accuracy. Although it has been replaced in most of cases by next generation sequencing, it remains as a gold standard for a small scale project or validation occasionally for the next generation sequencing result. Next generation sequencing, also known as second generation sequencing, is a high throughput sequencing, massive parallel short read sequencing. It's a deep sequencing. It allows that you could test the example, a lot of examples at the same time with low cost. And now it has replaced the Sanger sequencing in most of the cases. So the concept between, you hear the Sanger sequencing, next generation sequencing all the time, or you read the literature, they talk about this too, also all the time too. The basic concept behind this sequencing method are same. They use the DNA polymorphers as fluorescent nucleotide, one by one onto a growing DNA template brand. And they each incorporate nucleotide is identified by its fluorescent tag. The critical difference between these two sequencing methods is the sequencing volume. Sanger sequencing only sequence a single DNA fragment at a time, but next generation sequencing allow you massively parallel sequence many of fragments simultaneously per run. So now we have 3 applications of next generation sequencing. One is targeted genes panel, like renal side we often use. One is exome sequencing. You hear exome sequencing, the technology behind are same. It's just that the coverage is different and the probes are different. So exome sequencing, they sequence all the genes, but only sequence the coding area, the exons. The whole genome sequencing sequence all the genes, they sequence both coding and non-coding area, okay? So we talk about the copy number variants are often, are also important. So how to detect them? There are majorly 3 technology you could consider. One is called microarray, and second is called multiplex ligation-dependent probe amplification, also known as MLPA, and third one is NGS-based copy number analysis. So microarray is a high resolution. We thought it's high resolution before, but now we know it has limitation. Like here we showed is for those, the only target on the 50 to 200 kilobase. For those less than 50 kilobase, you might be missed by the array. It's a genome-wide screen for the copy number variants. It could simultaneously and rapidly evaluate the southern of regions along the genome. Usually the turnaround time is about 2 to 3 weeks. There are 2 major types, the SNP array and a comparative array. I will skip this detail about this technology here. The microarray has been used in diagnosing genetic kidney disease. At this study, they assessed over a cohort of 123 patients, and they identified 4% of patients have a copy number variants that cause the genetic disease. Next one is MLPA. By the name is probe, is use the probe and only target on the regions designed by the probe. Compared to the chromosome array is a genome-wide. The MLPA is exon level copy number variant detection. we talk about next generation sequencing is outstanding technology to detect single nucleotide and small insertion and deletion. Historically, they have some challenges in identifying copy number variants because of the short reading probe and also the GC content bias. However, great news is that now they are able to overcome the technology barriers now. They have showed high sensitivity and specificity in detecting the whole gene deletion, like the one Dr. Rastogi showed, the whole gene deletion in HF1B that could be picked. You possibly, if you order a lot of panel, you possibly see some, they even reported you, some patients have Klinefelter, actual copy of X chromosome. This can be picked by next generation sequencing. Previously, it's hard to do. You had to do the chromosome analysis or chromosome array to do that. And also, it has showed excellent performance in picking the single or multi-exon level deletion and duplication. Particularly, next generation is also sensitive for detecting copy number variants less than 50 kilobase. We talk the chromosome microarray is not able to pick this level, this size of the copy number variants, but it can be picked by the next generation sequencing. Although next generation sequencing has some limitation, like it's hard to detect these variants in the pseudogene area or the fusion genes or some insertion in the high repeat area, like Dr. Thomas commented this morning. Overall, it has showed reliable performance in detecting 3 types of genomic variation. So by understanding the technology, you could think of your testing that you could use in your patients. You could do the NGS-based panel, like the panel you have used a lot, or whole exome sequencing, whole genome sequencing. Sanger-based testing now often limit to the single gene test or just a 2 to 3 gene test or the targeted variant test because of the cost effectiveness perspective. If you have some suspicion after the next generation sequencing test, you have some suspicion for the copy number variant. For example, some patients have congenital anomalies or kidneys with actual renal manifestation. You might consider, oh, this might be a copy number variant that was missed by the next generation sequencing. You may consider the chromosomal array, or you have some concern about the pseudogene performance of the NGS or some insertion in the high repeat area. You might consider doing other tests. This, I would say, this might be the time you consult the genetic service. Okay. So by the labs designed the test in an easier way for us to use. Based on the number of the genes you could detect, they design that into targeted mutation or variant. For example, you have a family, they know what genetic change, what variant caused their family issue. You can only test this specific variant for your patient. All single gene test, all panel tests. Panel tests that can be phenotype guided like FSGS panel, hypokalemia panel, or you could do the broad genes panel like renal side. Or you could consider doing the whole exome sequencing or whole genome sequencing if your suspicion may remain high. This test, they have their pros and cons. Of course, when you do the only target on 1 or 2 or small number of the genes, they have high sensitivity and the cost usually lower and the turnaround time might be quicker. However, when you do the large gene panel or the exome or genome sequencing, you are sequencing a lot more genes, you sacrifice a little bit the sensitivity, and also you might face the challenges that you have some uncertain testing result like variant or uncertain significance, or you may have the incidental finding, like you have some patient reported with a cancer gene. So of course the cost will be higher and the turnaround time will be longer. For the exome and genome sequencing, usually costs more than 3 months to get the result back. So in our renal genetic clinic from Cleveland Clinic, we have used multiple testing modality with genes panel most frequently used, just like in your practice. We also did some testing with chromosome microarray, single gene test, or exome sequencing test. So I'm sorry again for running short on time. I would make a summary of this talk. What we have learned from the history, the collaboration, the innovation, and advocacy for policy change have shaped our history. And I believe this will guide us to a brighter future. The family history is critical for diagnosis of genetic kidney disease, have some basic understanding of the pedigree analysis. Genetic kidney disease are caused by single nucleotide variants, small indels, and copy number variants. And the NGS has demonstrated great performance for covering small nucleotide variants, indels, and some copy number variants. And the clinical NGS-based testing in renal genetics include panels, exome, and genome. We have the panels are most frequently used, but if your suspicion is high, you might consider doing the exome or genome sequencing. With that, I conclude my talk, and thank you for your attention.
We're running short on time, so I'm just going to take the moderator's prerogative here and just ask one question. I work at a place where a lot of people probably do, where maybe they do or do not have access to genetic counselors or geneticists that readily. And so I was wondering, there's a lot of information and the nuances of when to order something other than what's probably the easiest for a nephrologist to order right now due to how things are set up. Is there specific patients where you would be going straight to whole exome or whole genome sequencing or chromosomal microarray or certain patterns of disease to focus on to make it simpler for more general nephrologists that don't have access to all the services?
Sure. Yeah. That's an excellent question. So our study has showed that after the panel test, we have about 13% increase in diagnostic yield during the exome and genome. For those, we analyze the characteristics for those patients, why they are picked by the exome but missed by the panel. We found there are two major contributors. One is the actual renal manifestation that really make the difference. Like the HNF1B, you also see these patients, they might have hypomagnesemia if you check. They have the diabetes from early onset. So if you look at the chart and look back, you see, oh, actually this is not a straightforward case. And also, of course, for those with dysmorphic features, you see even in the hallway, walking into your office, you see, this patient look different. The ears are so small, the eyes so different. The lips are not have some cleft of palate or small chin, or they have skeletal disorders syndactyly. This would be the case you need to consider. You might consider doing the whole exome or genome as first tier test. And of course, for those with congenital anomaly, also with intellectual disability and developmental delay, these are strong indicator for considering exome or genome sequencing. Because of the regulation for the exome and genome sequencing, you really need a formal consent. The ordering would not be that much straightforward like you order a panel test. You need to consent the patient about what the result would be, because you might have incidental finding the patient may got some cancer gene, BRCA1 gene, BRCA2 gene, or some cardiac issue that should be actionable by the American College Medical Genetic Guideline. You need to consent this patient. And also, as the data sharing, exome and genome sequencing data are always precious. And also, if the patient is interested in any future research, this is typically the consent you need to do. I know in our busy nephrology practice, this take you at least 30 minutes to get this done. I do not feel that we should put this burden on the shoulder of nephrologists. If you consider exome genome sequencing, you should refer to some genetic service nearby. Thank you.
are going to, so Andre Weinstock, Alport Syndrome Foundation, and I have an interesting story, and I think you might have answered it, but the challenge is, so we referred a Alport patient, well-recorded traditional history, the males with X-linked, but deep intronic. So missed, they go to Natera, it comes back as a negative result. Referred this patient, who was a woman, to interested in family planning, to what I would call a large university which had a very good genetics program. And the genetics nephrologist had to leave on an emergency, and she got referred to another doctor in the same clinic who said, oh, ignore this genetics mumbo jumbo. You're not an Alport patient. Alport only happens to men. In your succession planning that you sort of described in here, how do centers of excellence, how do you prevent something like that from happening?
That's a great question.
Any general advice? I know your succession is
yes,
well short.
Right here.
So.
No, I mean, it's a great question. I mean, and the answer, it's not one I have a good answer for. Unfortunately, I've had disaster stories like that referred to me. One 19-year-old who they got the wrong testing for anti-alpha galactosidase was what they wanted to order. They ordered alpha galactosidase, and they did it wrong. The enzyme activity was low, so the story that they called from their family practice was, hey, you have a genetic disease. We did the wrong test, so you don't want to have kids. You should be so lucky that we did this. And I'm like, first of all, and it was, she didn't have it, but I mean, I am all ears. I think the hardest part we have right now is getting people interested, right? I mean, so, first of all, we need to teach all nephrology fellows, everybody in nephrology, general nephrology, needs to understand basic inheritance patterns, right? And they also need to understand what they don't know, right? And so I think that's key, is training everybody for a base knowledge, which we don't do a good job of. Even in peritoneal dialysis, I sit on the home dialysis ASN committee, and 10 years later, after I've been on it, we are still talking about how do we educate fellows on home dialysis, right? And now we're adding genetics to it. But I mean, we got to do a better job of training people. And then we have to do a good job of planning succession, but planning succession doesn't solve that problem, because that problem is just a general knowledge and talking about things you don't understand. It's better for the patient if people just says, I don't understand, let me get you with the person that does, as opposed to talking about wrong information, because that takes us longer to try and correct it. But
thank you.
Yeah.
Hi, I'm CJ Zhang from California. Two questions. One is, I saw you have CKD with LVH. You recommend gene testing. That's a lot of patients. Second question is for Dr. Wang. After the gene panel, you want to do exon sequence. How do you order that?
So let's talk about CKD, because I put CKD with LVH, right? CKD plus neuropathy, CKD plus irritable bowel syndrome. The reality is, the reason I put that up there is that it's a lot of patients. I mean, honestly, people are talking about who should we do genetics panel, or who should we do it on. I'm thinking about who shouldn't we, because lots of times I can't look at a patient, I can't look at their kidneys and say, this could be genetic. We talk about other gene panel or genetic risk factors like NPHS. There's an emerging story that you used to need to have 2 copies of NPHS2 or NPHS1 to have disease. Well, it turns out you're probably at increased risk with 1 copy. Now, you don't get the congenital nephrotic syndrome, but you're at increased risk for kidney disease. So the reality is even in my clinic, I can't really tell who needs genetics and who doesn't to a good enough state that I can't necessarily think that everybody doesn't need it. And I wonder at some point if this is just, hey, you have CKD, I'm going to do the renal panel, I'm going to do urine protein, urine creatinine, and a gene panel. I think the only reason we haven't gotten there, and this is me on my high horse, which is one of the reasons we haven't gotten there is that genetics was new, right? And we have Genetics Information Non-Discrimination Act, right? And that's all to protect genetic information. But we've been diagnosing genetic kidney disease without genetics forever. Like, do you ever talk to your patient, I'm not going to do this ultrasound because I could actually diagnose you with a genetic kidney disease and it might affect your insurance. We don't do any of that for all of the things that we do. It's just because it's genetic and it was new and people put a bunch of regulations. So the question long term is, as the cost of genetics goes down, as the acceptance and the regulatory gets more reasonable, Now the question becomes is, should it be standard of care in everybody, given that I can't even say who needs it and who doesn't?
Yeah, we should. That's what oncologists.
Yes. Yeah. And I'll let Dr. Wang ask about the how to order whole exome.
Yeah, to be very honest, the last time I ordered by myself the whole exome sequencing was 13 years ago when I was a genetic fellow. The reason why, there's the easy way. If you plan to do the exome sequencing or genome sequencing, you go to the lab, they have a portal, you set up, you register, and then you can place order, yes. And then you can send the patient and have them sign. So that's the way to do that. But this actually, I want to follow your question to highlight the importance of the infrastructure setup and the support from your institute, from your department, your division. We have a well-established supporting staff team for me and for our genetic counselors. I just tell them we order this, then they get that done. And for similar thing for the pre-authorization, we have a team deal with that. So that make my life much easier. It's indeed like Dr. Gharavi highlighted that we need some upfront investment from the institute. We really need to convince the leaders this is something good for us and also for our patients. And down the road, like Dr. Wallace said, the clinical trial possibly bring some revenue to your institute.
Yeah, there's one other revenue source that, from the prior authorization, which is the revenue that people get from 340B and infusions, but that is only realized if your institution has a home infusion company. And so Rob Hopkins at Cincinnati was telling, as far as getting resources for their clinic, they said, look, yes, our clinic isn't making tons, but the institution realizes X on home infusions from Cincinnati. Ergo, they got resources to help with prior authorizations, et cetera.
Hi, Joshua Kaplan from Rutgers, New Jersey. I wanted to make 2 points, and I'll see if I can remember them both. The first point is when we talk about sort of establishing centers of excellence and getting genetics more into the mainstream, part of that might be improved by changing the way the genetic reports are issued. So right now, the genetic reports are almost incomprehensible unless you know what's going on. And there's no reason why that should be. There's no reason why people like you shouldn't be sitting with the people who are doing these tests and changing the words that go out so that regular people can look at the reports and understand what it means and what they should be doing with the results.
Right.
So that's thing one. Thing two is that, your talk, my takeaway from your wonderful talk is that rare genetic diseases are not so rare. It's just that we're not looking for them. And the same thing goes with primary hyperaldosteronism, where I was taught in medical school it's vanishingly rare, and then I was seeing it all the time. But it's because now we know to look.
Right.
And it's going to be the same thing with this, and that's fascinating. But the other part of it that we haven't really gotten to yet today, and I'm really interested to see it, and maybe it's going to pay for the really expensive exome sequencing, is the idea that it's not just for the rare diseases, it's for all of the people with CKD that we're going to be prescribing goal-directed medical therapy that is probably $20,000 per patient per year. Who's going to respond well to it? Who's not going to respond well to it? Who should we be spending the $8,000 a year for the SGLT2 inhibitors, and who should we not? And that's going to pay for a lot of exome sequencing, I think.
Yeah, it's going to be interesting. Two parts of that. One is polygenic risk scores, and the other is pharmacogenomics, right? And for a long time, pharmacogenomics, at least for our insurer in Alabama, 80% of our commercial is Blue Cross Blue Shield. They stopped paying for pharmacogenomics because the return, right, is that the genetics were expensive, the return on savings was small, right? And there's been other examples even before we had widespread genetics, and I'll give you one, which azathioprine. So there was a mutation that if you take azathioprine, it's a 1 in 3,000 shot, you develop leukopenia, but it turns out that was 1 in 3,000. If you tested every single person for it, the cost was enormous. So London, or England, was the first person to say, we're not doing that, right? So what we have to do on pharmacogenomics is we have to get much more data on what is the return in a resource-constrained environment, right? So with monogenetic disease, it's a lot easier, right? But you're absolutely right, which is as genetic costs go down, is it, I mean, honestly, you just wonder at some point, are you just, sequenced at birth and then, that data is just there forever? That's probably, 50, 100 years from now. But still, yeah.
What about his previous question as to how the rhetoric that comes on
Oh, the rhetoric is interesting, and it's probably, it's mainly because genetics is not hard and fast still. I mean, we are still learning. So probably the easiest is pathogenic versus not pathogenic, right? The pathogenic, yes, it's pathogenic. Now, what do you need to do about it is not something that a gene panel company can say. They are not there to give you recommendations. They are there to give you the diagnosis. They take on different liability if they're telling you what you should do, right? Where it gets even harder is when you start getting variants of unknown significance, carrier states, et cetera. But I think that and there are some people that actually just say, I don't want to know about the variants. I don't want to, just give me pathogenic not. But it's going to have to take something else to say, what are you going to do with this, right? And I don't think the gene panel companies or the gene companies can tell you ever what to do. Now, there are interesting things that are coming, like something called lookalike. So in EPIC, there's a program called the lookalike program, which says, look, you've diagnosed your patients with X. These patients are grouped with this doctor. Why don't you send them to that doctor and they can figure it out? So establishing referral programs through the lookalike program is probably the next best thing.
Hi there, I'm Dominic. I was just want to comment on your thoughts on adding genetics into fellowship. I'm actually the inaugural renal genetics fellow at University of Iowa with Christy Thomas. I'm the first renal genetics fellow. I did my general nephrology fellowship in Utah and transplant fellowship in Utah, so it's like I'm like PUI 7 at this point. I'm really rare that people want to do this much fellowship. I think most of my co-fellows already 2 years in nephrology is already seems like enough. They want to go to the real world. I wonder what your thoughts are on trying to make a 3-year program like pediatrics and how it's going to affect people going to nephrology, as we already have a big shortage of people wanting to do nephrology. So.
Well, I think this will be an add-on. And I think there's enough people interested now that we could do it. Then you got to get it funded, right? So there's companies now that are starting to fund these fellowships, because it's not cheap to fund an extra year of fellowship. You got to find the person, and then you have to have criteria on, well, just because you went through this extra year, how do we say you are certified to do renal genetics? And importantly, then you have to say, well, what is the job, right? Because it's harder to invite people to do an extra year if you say, well, after this year, well, there's going to be jobs out there for you that are for renal genetics, right? And I think now we're in a much better place. So I am not opposed to a third year if it is an elective third year for the nephrogenetics, and that's what I think we should do. I think we should say this is general nephrology, this is nephrogenetics, this is genetics. That is the tiers of what we should do right now.
Okay.
Yeah.
I would say, if you want to move to Cleveland, we can talk.
Yeah.
Thank you for your comment.
Although Alabama is much warmer.
I went to medical school in Texas at Galveston, so humidity is a little bit too much for me.
Hi, I'm Rajat Maheshwari. I practice in Akron, Ohio. So a couple of questions for a private practice nephrologist. One is whether or not to request variants of uncertain significance. Two, when you do, I have, generally speaking, requested those. I've had patients who have the manifestations of disease, but it comes out to be variant of uncertain significance. Now, I speak with the company that ordered the test, and they would say, oh yeah, you'll have to get 3 family members tested to get that gene, categorized as a pathogenic gene. I mean, how is a private practitioner supposed to help advance science there? Second question, if I may ask, would be relating to autosomal dominant variants of uncertain significance, but not manifesting in the patient. And maybe hopefully you can say something about Revel scores and what a general practice nephrologist needs to know about those and how to help interpret those.
All right. Well, so based on the ACMG, you're only going to be held to treating those that are pathogenic or likely pathogenic, right? So those are simple. But when you have somebody, and I have identified at least 2 families with Fabry that were VUSs, and you do the kidney biopsy and there's chakra block full of zebra bodies, et cetera, I personally, this is what I tell my colleagues in Alabama, always get the VUSs. Not that you're going to use them, but always get them. Because as soon as you're interested and you look down that list and say, this explains the patient, even if you're not going to handle it, you have something to send to the nephrogenetics, because that's the first place I'm going to look, right? And if you don't have it, I can actually request it from the gene panel companies and say, look, this patient clearly has something genetic, give me the VUSs, it wasn't reported, right? So I do think I would always get them. You're not going to be held to them medical legally. All you'll be held to is the likely pathogenic or pathogenic. And then I do think that no general nephrologist, no private nephrologist is going to have the time to resolve VUSs. That has to be done at the next level. And hopefully we can establish a referral network that you say this is the nephrogenetics clinic that will, and this is why I am sending to resolve this VUS.
Actually, in our study, we did a analysis for the VUS. We found that about 5% of patients over last 3 years have been reclassified. And of these patients, 75% got upgraded from VUS to pathogenic or likely pathogenic. So I agree with Dr. Wallace. We should include the VUS. Maybe you are not immediately changing the management for the patient, or I don't know how to handle this, but at least you have this data available for the patient. Because once you see, I don't want the VUS, it's hard to go back to just a request the VUS to be released. Sure. Yeah, that is a lab system. It's based on, there are actually different algorithms that the lab could use to tell you this is the likely pathogenic or the VUS or benign. Is usually they consider 0.7. If I remember correctly, they consider more likely. But it's not the only way. But there is some other things that there is there is a software, AlphaMakeSense. It's based on the AlphaFold by Google. They actually could have pretty good negative predictive. We have not published this data, but this is something we have learned. It could help you to consider this possibly be reclassified or not. Yeah, Ruffle score is one thing you could consider.
I think we have to eat, but no, Rashid. Yeah, go ahead, Rashid. And people can start, but I would like to hear your question, Rashid.
So,
yes.
Just to back what Dr. Wang and Dr. Wallace said about VUS, I don't think the solution to that is not to say that, I don't want to see results with VUS. This is the way in which I look at VUS. Most of the VUS is because the person doing the genetic testing doesn't have the detailed phenotype. When you get the VUS, you have the advantage that you have the phenotype. You can look at it deeply, and that's what is called reverse phenotyping. So you said 5% in 3 years in your clinic. In typical pediatric clinic, 10 to 20% of the VUS that we get, based on the phenotype, we were able to say that this is actually